How you doing? I'm Mr. Rose, and today we're going to look at an electric force, or I should say the electric force, due to a uniformly charged ring, that's a three-dimensional ring, and some positive test charge some distance above. So what are we going to do? First, let's define our parameters. Our parameters are, I'm going to say that this ring of charge has a radius r, and like I said, is uniformly charged positively. I'm going to say this charge up here is a positive test charge, charge q, and it is directly above the ring, in the center of the ring. So I have a three-dimensional ring that's sitting like this, and I have this pink line, which is coming from the center of my ring, as my z-axis. So this test charge is some distance above in our three-dimensional space that I'm calling a distance z away. So what we want to do is I want to find out how much force this entire ring is implementing on that charge. To do that, we're going to have to think about a couple things. I'm going to skip this green for a moment, and I'm going to apply just straight Coulomb's law. We know Coulomb's law is equal to 1 over 4 pi epsilon naught, that's our constant, times the two charges, Q1 and Q2, divided by the distance squared, r squared, all in the r hat direction. Remember, because the Coulomb force, the electric force, is a vector, so I do need that r hat. Well, this equation that I have, this general expression, is for just two distinct charges. It is this charge, or that area of charge, that single charge, and there. We know that this ring has multiple charges. I have a charge, and 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 a charge. So we're going to use something that we've used in the past. Remember, charge, very much like mass, is a property of matter. So in the past, we've defined something, lambda, mass per unit length. Well, here I'm not worried about my mass, I'm worried about my charge. So I'm going to define a charge per unit length, which I can rearrange, and I say Q is equal to my lambda, my charge per unit length, times however long my ring is, or however long my charge distribution is. So I have Q equals lambda times dl. I'm going to sub that directly into my expression. So now I have a force for 1 over 4 pi epsilon naught, for, again, that single charge, lambda dl, times q, my second q, over my radius squared. My radius was r, or r squared plus z squared, and we know that from Pythagorean theorem. Again, this is just for one piece of charge. We know that we have charges all over the place. I have a charge, and I've drawn two of them. I've drawn what direction the force would be from that side, what direction the force would be from that side. And if I do that all around, we'd get this three-dimensional TP kind of effect, where we could see that all of my net charges in most directions are going to cancel out, and I'm going to be left with a net charge of only the z direction. So for my net charge in the z direction, I need to figure out what that is. My z direction is just z over the square root of z squared plus r squared. So when I take that, and I should be able to see that and make my symmetrical argument for that. When I take that and plug that into my equation in my r direction, really, I have my force, lambda dlq times r squared plus z squared, times that z direction. Now, if we notice, that z direction is really a factor of cosine. It's, if I throw in a theta over here, I know a theta over there from my alternate angles, I think that is, or vertex angles, that's actually what those are. I see that this is a factor of the cosine, so that makes sense to me. When I now plug this in, there's my direction. I simplify through, I have 1 over 4 pi epsilon naught, lambda dl, q times that z. My two denominators multiplied are r squared plus z squared to the 3/2 power. Now this is my general expression. We see this df, so we should and we see this dl, that should remind us, like, we need to do a little bit of integration. So what I'm going to do is I'm going to sum up all of the forces, because we do know that Coulomb's law is subject to the law of superposition, just like every other force. So I'm going to sum up all of my df's along that length to get my total force from my ring. So my antiderivative of df in the z direction is equal to my antiderivative 1 over 4 pi epsilon naught, lambda dl times q times r squared plus z squared to the 3/2 power. I may have forgotten the times z at the top. And I know all of this is constant, except for dl. So I pull all of my constants out. I have my antiderivative of df in the z direction is just f in the z direction. All of my constants times the antiderivative of dl. Well, dl is a loop, and a loop should make me happy because I know my length is 2 pi times r, so that's why I have my little smiley face. So now that I have a loop, I need to remember something. What did I do? I subbed in this lambda, and I know lambda is a charge per unit length. So that's a charge per unit 2 pi L, which means my charge Q that I subbed out before is equal to lambda times 2 pi L. That means I can sub right back in. I can put everything together, and where I have Fz, 1 over 4 pi epsilon naught, Q times Z times R squared plus Z squared over 3/2 power, times lambda 2 pi times R. That was just my direct substitution. I'm going to take that. I'm going to take my lambda 2 pi times R, gathering my constants, or my variables rather, and bam, throw myself a Q in there. So now I have my force in the Z direction due to this ring of charge, 1 over 4 pi epsilon naught times Q, little q times big Q, that's my little q, my charge is there, times Z, all over R squared plus Z squared to the 3/2 power. That looks great. How do I know that's right? How can we check that? What do you think? You in the blue shirt, what do you think? All right, that's close. Red shirt? That's right. If I make Z much, much bigger than R, well, what's going to happen? If I keep getting further and further and further and further and further away, it would seem like it was just a point charge, some point particle. And if I make Z further and further and further and further and further away, R essentially becomes no big deal, and I'm left with a general expression of Coulomb's law, KQQ over R squared. That's all I have for you today. We're going to utilize similar tricks to this as we get into more difficult problems and examples. Please feel free to like, comment, and subscribe, and I will see you next time.